Hello everyone. So today in this video we will talk about choosing ML models and assessing the quality of the models through some performance measures. Okay? So we will talk about the F-test, the R-square. We already know it from SLR, but we will now talk about the R-square adjusted, and we will talk about hypothesis test for beta J's. Okay. Um, so, um, okay. So first we will start with the F-test from the ANOVA table. Okay, just remember the F-test, the hypothesis of the F-test, it says that, well, all of the betas are equal to 0, right? So what does this mean? Beta 1 was the coefficient of x1. This is the coefficient of x2. This is the coefficient of xk. Hence, this hypothesis says that, well, y does not depend on any independent variable x's. Okay, so as x increases, well, it doesn't make anything on y. So as x2 increases or decreases, it doesn't make any effect on y. As as xk increases or decreases, it doesn't have any effect on y. Okay, so the hypothesis says that, well, the dependent variable y does not depend on any independent variable x's, or the independent variable x, none of them just has an effect on the value of the dependent variable y. And what's its alternative? Its alternative is at least one of them is not 0. Okay, at least one of them. I don't know which one, but it says that, well, at least one of the x's has an effect on the value of y. Okay, so okay, just look at this one. Look at this ANOVA, right? This table, the I don't know, the yellow one, right? So remember here I have the degrees of freedom. This is 3 because I have 3 x's. Remember our example, we were talking about the effect of the ingredients of the food. Okay, the effect of the ingredients on the like ratio of the food. So it was meat, vegetables, and spices, right? So there were 3 parameters to be estimated. That's why I have 3 here. And the total degrees of freedom was n minus 1, right? There were 13 different experiments on this, 13 many observations on this experiment. So the sum should be 12. That's why I have 9 here, right? So this is the sum of squares. Remember, this is SSE, right? This is SSE. This is this is SSR. Sorry for this. This is SSR, SSE, and this is SS total. And this is the SSR divided by degrees of freedom. This is the SSE divided by degrees of freedom. This is also what? This is also S squared, remember? See this? This is my the sample standard deviation S, and this is S squared. And if you just divide this by this, I have the F value. This is the F observed, and this is the significance of this F observed. Okay, okay, that's great. So it turns out that the value of F observed is 13, almost 31, and its significance level is its p-value. Sorry, this is the p-value. Okay, the p-value is 0, which means that you can clearly reject the hypothesis. Again, what was the hypothesis? It says that all of the x's are 0. So you say that just reject the hypothesis because my p-value is 0, right? The p-value is 0 here. So I say that, well, I can say that at least one of the x variables has an effect on the value of y, okay? So, okay, great. So in general, how can we reject f? So here's the significance is almost 0, but in general, you can just take the value of f alpha. So remember, this is my f random variable, and this is my f random variable. What you do is you just pick a critical value here. Sorry for this line right now. So this is what this is, f of alpha with k degrees of freedom. K comes from here, okay, k, and n minus k minus 1 degrees of freedom. So this is n minus k minus 1. So it's here, 9. Okay, so this is 3 and 9. And it leaves an area of alpha to the right. Okay, so this is alpha. So if your f observed, right, if your f observed is greater than this critical value, you can reject the hypothesis. So here we are safe because the p-value is already 0. Hence, we can safely reject the hypothesis. So, okay, so that's what we talked about. So the next thing is the R square. Remember the R square, the coefficient of determination. So R square here is 0.91. So remember what was it? It was the total variation in the data, right? And SSR, so this is SSR. So this is the variation defined by the model, right? So remember this is Y hat I minus Y bar, okay, squared, we just sum them up, and this is the total deviation, Yi minus Y bar. Okay, just remember our discussion. We said that there were two important things that we measure. The first one is the center of the data, and the second one is how much the data is scattered around the center, right? So this is the total deviation around the center, and this is what I predict through the line, right? And this is the average. So this is the deviation that I can explain by my prediction, with my prediction, okay? So if this was the R square, so since R square is 91%, well, we say that the model can explain, sorry, the model can explain 91% of the variability in the Y values. Okay, so 91% is explained by the model. So, okay, well, all of the variables are in the model, and so in fact, choosing the best model, okay, best model does not necessarily mean that you have a large R square, okay. So the largest R square is the model. Sorry, let me just rephrase my word. So the best model has the largest R squared is not a correct, let's say, statement, okay? So the best model has the largest R squared is not a correct statement. Because, for example, assume you have x1, x2, and x3, well, assume that you just remove x2 and x3 from the model. And you see that, well, only x1 with x1, only with x1, the model is able to explain, let's say, 90%, 5%, sorry, 90.5% of the variability in the model, okay? Then, well, there is no need to put two extra variables here, which is just adding two variables give you an additional worth of 0.5% variable, okay? So managing the model with additional two variables is hard. So a model with a single variable is always better than a model with multiple variables. So there is a trade-off here, okay? So you want to keep, well, let's say you want to keep less variables in the model, okay? Because if you have less variables, then the model is more manageable, right? More manageable. But you want high, let's say, explanation, high, let's say, R square, okay? Maybe R square, let's say, okay? So this one just pushes you to keep more variables, because if you have more variables, then more variables just make you, just enables you to explain more variable. But as I said, if you have more variables, then it is hard to manage them up. So there is a trade-off between keeping more variables and managing the model and keeping more variables. That's it. So, well, we cannot say that this is the best model, because the best model is not necessarily the model has the highest R square. So there may be some variables which are not significant. So what does this mean? This means that, well, if the variable is not significant, then its beta is not significant. What does it mean? If its beta is equal to J. What does this mean? It means that, well, using the corresponding xj, okay, corresponding xj is not a good idea for predicting the new future values. So you should just remove it from the model. Okay. Or there may be some other term that could be added to the model to make it fit even better. Okay, so we don't know. Maybe removing some variables is good, or maybe adding some additional terms is good. So in fact, we don't know it yet, right? So there is a new thing called R-square adjusted. Okay, adjusted R-square. So what is this adjusted R-square? Remember our R-square. Our R-square was equal to SSR divided by SS total, which is equal to, instead of SSR, just write SST minus SSC. So it's equal to 1 minus SSC divided by SSR, right? So instead of this, what we do is just divide SSC by what? By its degrees of freedom, n minus k minus 1. Okay, just go back to our ANOVA table. I don't know whether I have its original one. I don't have it. Okay. So just look at here. This is SSC, okay, and this is n minus k minus 1, right? N minus k minus 1. And this is what? This is n minus 1. So what you do is just divide this one by this one, sorry, this one, so this SSE by this, and this one by this, okay? And find the adjust R square. Okay, so adjust R square here is 1 minus 38.68, okay, divided by 9, right, and 438.13 divided by 12. So this is my R square adjusted, right? Great. So what is R square? R square, so this is R square adjusted. What is R square? R square is 1 minus 38.68, 438.13, right? And this is my R square, okay? That's the difference between the R square adjusted and R square, okay? So in our example, R square is 0.91, okay? And R square adjusted is 0.88, okay, 0.8813. Well, generally, R square adjusted is a better estimate than the coefficient of determination. So why? Because, so assume that you are just making a regression y versus, let's say, 10 many x variables, x1, x2, dot, 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 x10. So if you just make a regression using y and x1, let's say you have an R square. Let's say this is R square 1. If you just make a regression with x1 plus x2, okay, then you have, let's say, R squared. Let's say this is 2, okay, this is the second one. Generally, not generally, it's always, if you add a variable to the model and make a regression, okay, so let's say this is x1 dot x2 dot x3, okay, that y x1 plus dot x10. So this is, let's say, R squared 3, and this is R squared 10. So always adding a variable increase. Okay, let me just like this. Let me just write it here. It's always the full model's R squared is greater than R squared 9, R squared 8, R squared 1. Okay, so if you add a variable, always R squared increases. Okay, but the thing is that, well, adding a variable means you have a less manageable model. Okay, so is it worth adding a variable to the model? So because you add a variable, you just make it more unmanageable. Well, adding this new variable has a significant contribution to R squared or not. That's the key thing to us. Okay, so R squared adjusted is just making this, let's say, just measuring this additional R square. Okay, so what happens is that it's not the case R square adjusted. Okay, I'm not sure, it can be, but it can be not adjusted 10. It can be, or it cannot, it may not be greater than adjusted R square of the model with a 9 variable. Okay, you cannot clearly say this is larger than. okay? So there are some cases when you just add a variable, well, your R-square increases, but your R-square adjusted does not increase. So if you add a variable and if it turns out that your adjusted R-square does not increase, it means that, well, adding that variable is not worth it, okay? So it's not worth to add that variable, okay? So the next thing is just making a hypothesis testing for beta J, okay? So in fact, we know this, but in multiple regression, well, we will see how we can manage this hypothesis testing for beta J's. So the first thing is, of course, we may just make this test. Testing beta 0 is equal to 0 versus beta 3 is not equal to 0, right? So, okay. So I don't have that table there. Just give me a second. Okay. So I just put it there. Well, I want to test whether beta 0 is equal to 0 versus beta 0 is not equal to 0. Remember, the first line is just for this hypothesis testing. So the coefficient beta 0 is 39.16. Well, its standard error is this. And this is your T observed. Remember, this is the T observed. T observed of what? T observed of this hypothesis, right? So, okay. So it's associated p-value 0. What does this mean? Well, you can reject the hypothesis. You can reject it and you can conclude that, well, beta 0 is not equal to 0, right? So it shows that the intercept is significant, okay? Well, okay, we reject the null hypothesis and say that, well, beta 0 is not equal to 0. Similarly, we will look at the tests for beta 1, beta 2, and beta 3, okay? So, well, the next test is whether beta 1 is equal to 0 or not. So this is my T observed value and its associated p-value, which is 0 there. So I can again safely say that, well, variable x1 is significant, hence we just reject the null hypothesis and say that, well, beta 1 is not equal to 0. Okay, so it's significant, you can just use it in the model. So what does this mean? Another explanation is it explains the good portion of the variability in the y values. Okay. And the next one is whether beta 2 is equal to 0 or not. Okay, this one, whether beta 2 is equal to 0 or not. This is your T observed, and this is your p-value. Again, you say that, well, keep beta 2 or keep x3 in the model. And the last one is test whether beta 3 is equal to 0 or not, okay? So this is your T observed, and the associated p-value is 0.59, okay? So what does this p-value say? Well, it's not close to 0, hence you can not reject the hypothesis, okay? So you cannot reject the hypothesis. So the variable x3, okay, does not have a significant contribution to the model. Hence, we can just remove x3 from the model, right? So remember, our model was y that's equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, okay? So this one says that, well, beta 3 does not have a significant contribution to the model. So you can just remove x3. And this is the remaining model, okay? This is your remaining model, right? Now, we will fit this model, okay? We will fit this model. What does it mean? Just do everything from scratch, okay? Just start from the beginning and make the regression using only x1 and x2. Start from beginning, right? Beginning and regress using what? Using x1 and x2, okay? Just remove x3. Well, so, okay, one thing to remember is, okay, so, okay, so when we decide to remove a variable from the model, so we get a new model to fit a new calculation. Okay, so everything starts from the beginning, as I said. So we need to run the regression for this new model, right? This new one. Okay, so just okay, for this model. Now note that the SST, what was SST? Let me just write it, was yi minus y bar. Okay, square, just sum them up. This won't change because your observed variables and your average does not change, right? But SSR, hence, if SSR changes, since sum of SSR and SSE is equal to SST, it will change. Why SSR change? Because SSR just depends on what? Depends on the regression line, okay? Since it depends on the regression line, it will change, hence SSE will change, okay? And we will see which model is better than the other one. Now note that the X matrix has changed and it has dimensions of n times 3, not n times 4. We will see it in the following model. And the new one, so you have X transpose X inverse, X transpose Y. It turns out that the new coefficients are given like this, okay? So remember, this was the original one, X1, X2, X3, and this is Y model, and this is my X matrix, right? It doesn't look like a matrix, but just, okay, 1, 1, dot, 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 1. And then I have 174, okay, which comes from here. So I just put it here. Okay, so let me just write it like this. This is x0, 1, 1, dot, 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 1. Okay, so this is my matrix. This was my X matrix. Okay, sorry for that. Now I just remove x3. Okay, now this is my new X matrix. 1, 1, dot, 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 1. Okay, this part and this one, right? So this is my new X matrix. Hence, all of the calculations change. Remember, B was equal to X transpose X inverse, right? Times X transpose times Y. So since X changes, B changes. Okay. So, well, this is the new result for the new model. Okay. So I have, this is again my beta 0, my beta 1, and beta 2, but these are the updated values. Okay. Just look at this one. This is 1.03, and the old one was, sorry, old one was 1.02, and the coefficients, the beta 0 was 36. Now it is, sorry, now it is 36, but it was 39. And x2 was minus 1.86. Now it's almost there. It's minus 1.87. Okay. Now just look at the p-values here. So whether removing this beta 0 or beta 1 or beta 2, can we remove them? Well, it turns out that their p-values are 0, hence we cannot remove them. So this is a good model, right? But remember, in the previous model, I have 0.59, which was the x3 variable. That's why we decided to remove x3 there. Okay. And again, just look at my SSR, so SS total here. So this is the S total of the old model. Let me just write it there, old model, okay, and let me just write here new model, okay. So the old model 438 here, okay, and this is regression, right? SSR, and this is the old SSR. As you might see, the old SSR a bit higher than the previous one. Okay, that's only a bit. Okay, and this is the residual bit is 40 there, and this is 38 there, and the old one has a smaller SSE there. And okay, let's look at the adjusted R square and R square. This is the old model. It's 0.91 R square and 0.88 adjusted R square. Sorry. And this is the new model. As you see, well, the R square is almost the same, but we know that the old model is always larger. But it turns out that the adjusted R square increases. Okay, you see? So in the old model, it was 0.88, which is smaller than 0.89. That's the new model, right? So in the new model, we just removed a variable, and it turns out that, well, so the new model has a larger R square, adjusted R square. Okay, so what does this mean? This means that, well, the model with fewer variables, okay, with less variables, is better than the original model in terms of the adjusted R square. Okay, so that's why we just look at the R square, that's something good, but we also use adjusted R square to evaluate the models in between, okay? Just to compare the models. So one important thing is that, okay, so let's remember, we just make this hypothesis test, whether beta 1 is equal to 0 versus beta 1 is not equal to 0. So if beta 1 is not equal to 0, well, remember, this is my model, right? Beta 0 is beta 1x1, beta 2x2, and beta 3x3. So this hypothesis refers to the full model, okay? The full model. How about this one? Beta 1 is equal to 0. What does it mean? It means that, well, I just think that, I just assume that, I just conjecture that in my hypothesis, beta 1 is equal to 0. Beta 1 is equal to 0 means that, well, beta 1 is equal to 0, hence I don't have it in my model. So this beta 1 equal to 0 refers to this model, okay? The model where you already have the intercept x2 and x3, okay? Again, this hypothesis beta 1 is equal to 0 refers to the model where you already have x2 and x3, but you don't have beta 1, okay? And beta 1 is not equal to 0 refers to the full model. So what you do in the hypothesis testing is that whether adding, so whether, let me just say this, is adding x3 over existing x1 and x2 worth, okay? Is this worth? Sorry, for this one, sorry, this is x2 and x3, sorry. This is x2, x2, x3, so this is x1, okay, this is x1. So this hypothesis just asks whether adding x1 over x2 and x3, is it worth? If it is worth, you say that, well, I reject the hypothesis, okay? I reject the hypothesis, which means that you reject this model and say that you can use this model. If you cannot reject this hypothesis, okay, it means that, well, I cannot reject the hypothesis and please use this model, okay, the first one. So remember what we did in the last slide. So in this ANOVA, we just removed x3, right? So in fact, what we did was just beta 3 is equal to 0, which means you have this model, beta 0 plus beta 1x1, beta 2x2, versus beta 3 is not equal to 0, which is the full model, right? Okay, which is the full model. So what we did is you just not reject H0. Okay, remember we do not reject H0. So what does it mean? Do not rejecting H0, please use this one. But for X1, just go back. So just go back, just look at here. Whether you just test whether beta 1 is equal to 0 or not, well, you just reject the hypothesis with this p-value. So what does this mean? It means that, let me just change my color so that it means that you just reject this model and you say that, okay, instead of this model, please use the one which is the model of the alternative hypothesis, okay? So in fact, that's the key point in testing the hypothesis for each beta 1, okay? So testing the hypothesis is just referring to, testing a hypothesis just refers to whether adding this one, okay, to the over the other variables, is it significant or not? That's what we are doing in hypothesis testing for single betas, right? So the SSR increases as the number of parameters go up. Okay, so in fact, this is very parallel to R square. So we cannot use direct SSR in choosing model. So we have two performance measures, which is adjusted R square, okay, and the other one is the mean square error. Okay, the mean square error, what was it? It was SSE divided by the degrees of freedom. Okay, and the degrees of freedom is, remember, it was n minus k minus 1. Okay, so just look at the previous model. Just look at the previous model. So here, let me just change my color to, let's say, blue. Okay, okay, that's great. So here, just look at the standard error, which is this one. Okay, in fact, this is the S square, right? This is the, what, not S square, but S. So S here is 2.07. This is the old model, right? And in the new model, it's 2. Okay, that's great. It's smaller than 2.07. Okay, so the new model has a smaller error. Okay, so Using this criteria as well, you can say that, well, the new model where you just remove x3, so the new model is better in both criteria, okay? So what did we see so far? The first one is comparing R square, but it's not a very good measure. Then you have the R square adjusted. It's adjusted in the sense that whether adding a new variable, is it worth adding new variable by just looking at the contribution of it to the existing model. And then we also look at the mean square error, okay, which is the estimate for the sigma square. The smaller the estimate, the better your model is. Later, we will see some advanced criteria for choosing models or for comparing models between them.